Hello, I'm Dave Terry, and I'm at the Elk Run Coal Training Center to give you a class today on high voltage relay. This is for the apprentice electricians to take their state certification test. And historically, this portion of the training, this portion of the test, has worried people more than any other portion. And it's actually among the easier of the practicals. And we're going to show you how easy it is here as we go today. First of all, let's identify some of the components. This is one of the state testing panels here that I've borrowed for the training, and you could very well draw this panel when you take your test. This is an actual panel, and it looks exactly like this, with the exception of I've added a couple of labels here for the purpose of the class that may not be present on the one you use. And the first things you need to know are what components are here and what they do. You have two relays. Note one of them is labeled 50G. The other one's labeled 51-1. Well, they're both time over current relays. Technically, they're both a time over current relay. A device 50, as you can see, doesn't have an instantaneous unit. It has only a time unit. Device 50 is for the ground, hence the G. It's supplied by the CT on the ground wire, this one here. The CT with the green wire passing through it from the ground resistor, that's the ground, supplies this device. Device 51. It's a device 51. It has both time and instantaneous. One is for overcurrent, one is for short circuit. The one, it's phase one. On a real substation out in the field, you would have a device 51-1, a device 51-2, and a device 51-3, one for each phases. On an underground station, you would probably only have two, 51-1 and 51-3. Now, it's supplied by the phase CT. The phase CT is multi-tap. There's more than one ratio available to you here. These go from a 10-1 to a 120-1. You choose the letter of the leg wire to decide what ratio you're going to be using. And this is real similar to a real-life CT terminal block that you would find in a station. Phase CT has one phase in it. A lot of young electricians are confused the grounding on the high voltage substations and the phase CTs with ground fault CTs, on power centers for ground fault on low and medium voltage breakers. It's not looking for an imbalance. It's monitoring the phase and reacting to the current that's on the phase, all currents, large and small. And it refers the current that it finds to this time over current relay, 51-1, and the relay compares the reading from the CT to the setting that you've chosen. And it, in turn, controls either a UV in the main breaker, the oil circuit breaker or vacuum breaker, or a shunt trip, whichever device you employ. The CT reports to, drives the time over current relay. The time over current relay, its contacts control a UV, and the UV in turn controls the circuit breaker. The ground fault CT, one ratio. Historically, customarily, it's always, not always, nothing is always, but it's usually a 50-5, 10-1. It's monitoring a ground wire. It reports only to 50G, one CT, one ratio, one relay. As you can see, we also have a button. It's called an E-stop. Some stations have an E-stop present on the control board. Not all do. But the e-stop on our underground units are at every high voltage installation. You would have a high voltage cable serving a portion of your coal mine being cared for by this breaker. This breaker provides the protection. These relays are adjustable that you can protect a length of cable, a circuit with this unit, and it will have a ground continuity monitor. And each one of those boxes, each one of those high voltage installations, be it a belt transformer, section power center, pump transformer, whatever, we'll have the ground monitor routed through the box, through an e-stop, and then through various lid switches on the box to control the unauthorized opening of a box, or to give you an ability to turn the electricity off, all of the power off at one time. When you push the e-stop, you're breaking the continuity of the ground monitor. The ground monitor controls the UV or the shunt trip, and the shunt trip and UV control the OCB or vacuum breaker. Oil circuit breaker, UV is under voltage release. Shunt trip does the same thing as a UV, only you have a different application. You put power to a shunt trip, it trips the breaker. On a UVR, you take power away, it trips the breaker. But they both do the same job, you just use them in different applications. And the e-stop, ground continuity monitor wired through the e-stop. You break continuity by pressing the e-stop, the breaker opens. Okay, we have OCB switches with lights that show either open or closed. OCB oil circuit breaker. Open means the power is off, the breaker is open. Closed means power is on, the high voltage circuit is complete, power is going through the breaker. These lights here show open or close. The red button is to open it, to turn it off. The black button closes it, turns it on. And we have a control breaker. Now, control breaker, it has nothing to do with the high voltage circuit per se underground. It's to protect the device, to protect the wiring of these relays. If you probably have a 20 amp control breaker that will operate the relays, it will supply the control power for the relays, and its only protection is for the wiring on the controls. It has nothing to do with the protection of the high voltage cable. So people confuse the control breaker as, when you have an under voltage situation, it trips the control breaker. Indeed, you test the under voltage protection by operating the control breaker. To simulate a power outage, you will open the control breaker to take power off the relays. Your OCB should open, and it should remain open after power is restored. And that exhibits under voltage protection. But the breaker doesn't provide under voltage. It's a thermal only breaker, similar to one you would find in your load center at your home. It's just to protect the wiring here. Now, of all the checks that are made, there are 3 that you must make every month there to satisfy the federal law. And there are 5 definite and separate protections provided by this unit. We're going to talk about these. You could be asked this as part of an interview type question for your state certification examination. And those 5 are, and it's easiest, particularly if you're a little stressed while you're testing or you're nervous, to look at the device. Don't try to memorize these and just chant them off, but just look at it and talk. You have short circuit protection. I generally start by the chart and work in a semicircular fashion and give myself a visual prompt. You have a short circuit protection. You have overcurrent protection. You have ground fault protection. You use the control breaker to prove under voltage protection. And then you have ground continuity monitoring. Those are the big 5. Those are the 5 that you could be asked on your test. What 5 protections are provided for by a high voltage breaker relay panel. Those 5. Now, you have to do 3 things for your monthly examination, at the mine site. And those 3 things are: you have to make a visual examination of the circuit breaker and its associated componentry, its auxiliary devices. Now, these are the auxiliary devices. You have a visual examination. That's 1. To complete a visual, you need to look at the circuit breaker. Sometimes, that's not, they're not readily in sight. You might have to take a cover off to view the circuit breaker. And what you're looking for is, obvious physical damage. You've got something hot, evidence of something being hot. You've got a breaking down of the insulation, a tracking. You've got a broken part, a missing part, a leak. An oil circuit breaker, is in an oil bath. And if the reservoir is leaking, then the part that suppresses the flash and insulates this breaker is leaking out. You're going to look for a leak. A visual examination, broken, missing parts, thermal damage, a leak, anything that's out of the ordinary, that's wrong. Now, next, the second thing you have to do is you have to do a manual operation of at least 2 auxiliary devices. Now let's talk about this. You're going to operate this thing manually versus truly putting a fault on it. A short circuit, that would be a phase-to-phase situation. Now you don't want to be there when that happens, a real phase-to-phase. That's a catastrophic electrical event. Assets will be damaged, and some of those assets, maybe human resources assets. You don't want to do that. So you want to simulate a short circuit. You want to manually operate this relay to prove that indeed, if this relay operates, it will turn the power off. You want to prove it has overcurrent protection. You want to manually operate the relay for overcurrent protection. And you want to prove that it has ground fault protection, that this ground fault relay will turn the breaker off. It will open the circuit breaker, turn the power off if you have a ground fault. And you want to manually operate this. You don't want to literally put a short circuit on your high voltage to prove this breaker works. You don't want to literally put a ground fault on it to prove that the breaker works. Now, manually operate 2 auxiliary devices. Make a visual examination of the breaker and all its components, looking for any broken or missing parts. Even something as insignificant as an insect nest could block the operation of this relay. I once had a problem with a spider had gained access into a relay and stopped the contact. You're going to be looking for those things. Another part of the visual exam is the setting. These breakers are wonderfully adjustable. The breaker relay panel is wonderfully adjustable. You see all these cable sizes here and all these different thermal ranges of the cables. You can adjust this device to fit any of those cables. But now, all those settings aren't correct. You're going to make a visual examination. You're going to check what size cable you have, and then set within those parameters there to not to exceed the approved settings for that particular size, insulation, and value, thermal value of the cable. All right, thermal rating of it. So that's all part of your visual and manual operation. Your last test, you can't perform from this location. If you're checking for monthly permissibility, this circuit breaker and its devices, you can't perform the final check from here. You have to go to the furthest point protected by this breaker and operate an e-stop to prove ground continuity to that point. If you break the ground continuity circuit at the furthest point, this breaker should fall. And you have to go to that furthest point and operate this e-stop. The e-stop is placed here for your convenience in testing. In real life, that's not going to be right beside you. You have to go to that point or have someone stationed at that point to operate that e-stop to prove ground continuity. Now we have a ground resistor at the source of all of our power circuits. The ground resistor, that's our number one safety device. You know, that protects you in the event of an insulation failure that involves a phase, an energized conductor coming in contact with the frame of any piece of equipment or the ground conductor on any cable. The ground resistor, it's going to resist the current. It's going to be an obstacle to the flow of current and limit the current because it's in series with the neutral of the transformer. It will limit the current to 25 amperes maximum, okay? And the voltage drop external to the ground resistor. The ground resistor is an electric machine. Now, it doesn't appear to be a machine like you would think of something that's got moving parts, you know, it will wobble or shake or do something. It doesn't move. It's static. It's stasis. It doesn't have any moving parts. But it converts any electricity that's on the ground conductor to thermal energy. It's an electric machine. It turns electricity into heat. And you size the ground resistor with its ohmic value and its current rating to accommodate the various voltages that you may encounter in a ground fault. Now this has to be tested. You have to take read the tag and see how many amps the thing is rated for. And then you have to use Ohm's law, read the current or read the ohmic value of the resistor, multiply that by the current, and that will tell you how many volts this resistor will drop. That figure needs to come within 100 volts of the value of any phase. So that if you have a ground fault, the ground resistor will deal with it and limit it to 25 amps and no more than 100 volts external to the resistor. I'm going to show you how to figure that later. Okay, we talked about all these different devices and the different protections they provide. Now let's talk about what decides our protections, what decides the level that we're going to protect, what level of current flow or what level of fault that we're going to interrupt. And with the 51-1, 2 or 3, the phase relays, that's determined by the cable size. You adjust your relays, you adjust your circuit breaker's trip levels to accommodate the size cable you're using. And there's several cable sizes listed here. And they're accepted ampacities. Okay? Now, this chart here is going to tell you pretty much all you need to know what level you can adjust your breaker to. Now, the 50G, that's for ground fault. What determines its ampacities, how high you can set it, is the rating of the ground resistor. The ground resistor is rated for a continuous duty cycle, 100%, 24/7. It's rated to deal with 25 amps, continuously. Now, as a redundancy, we're not going to challenge that ground resistor. By law, you're allowed to adjust the 50G to 50%, not to exceed 50% the ampacity of the ground resistor. Ampacity of the cable dictates setting the time over current relay for phases. The ampacity of the ground resistor settles for the ground fault relay. Okay, so you'll note all of these different ratios here. They're to accommodate the various settings for the cable. Here's how. Now this relay is virtually infinitely variable. It's got numerous taps. And you use the overcurrent tap, which is located in the rear. I'll be pulling this out here and showing you in a bit, as a multiplier times the CT ratio. And that says when this thing will trip. The current value is a product of the multiplication of the tap times the CT ratio. At that current, it will trip. Now, for the ease of our math, these relays are expressed in simple ratios at its most simple form, 10 to 1. You won't find a 10 to 1 relay. The second number will almost invariably be a 5. You'll have a 50 to 5, a 100 to 5, 150 to 5. And the reason we use that 5 is the 5 illustrates the ampacity of the secondary of the CT. There's an industrial standard for the ampacity of these CTs, these current transformers. CT is acronym for current transformer. The industrial standard is 5 amps for the secondary. The primary of this transformer is the phase wire or the conductor that passes through the window. Now the conductor, the phase wire or the conductor, some of them have a bar type CT where you bolt a phase wire on one side, it doesn't actually move through this, and you bolt the phase to the other side. Or there could be a hub type CT where cable entering this enclosure passes through a hub, through this CT. But the conductor that passes through the window is the primary. The winding of the CT is the secondary. The CT has an ampacity for the secondary of 5 amps. Now, it'll carry more current than that. It won't burn into and explode if you put more than 5 amps on it. But if you routinely and sustain a greater ampacity than it's rated for, then it may not respond in a linear fashion. It may saturate the CT. It's saturated with magnetism, and it may not respond correctly as you need it to. So we're going to limit all of our settings to a maximum tap setting of 5 on our overcurrent settings. Now, overcurrent and time go together. Short circuit and instantaneous. You'll note that the same CT provides both time, or overcurrent and short circuit. Time and instantaneous is both supplied by the same CT. In your overcurrent settings, they don't begin until 10. 10 is usually your first number for your core setting for short circuit. Okay? A core setting of 10 is the minimum. And on this device, it ranges from 10 to 80. Well now, that's a lot of current for that CT that's only rated for 5. What makes that an acceptable number, though, is the fact that it's instantaneous. There's virtually no sustained fault. That's the major difference between an overcurrent and a short circuit. They're both too many amps. There's too many amps for the conductor. An overcurrent is 125% of the ampacity of the cable. A short circuit can be a maximum of 600% the ampacity of the cable. So they're both too many amps. The main difference between the two is the magnitude and the duration of the event. With an overcurrent, it could be a lengthy time. You could, possibly could time this thing with a chronograph, with a watch. But with a short circuit, we're talking instantaneous. It's so fast as to virtually be no delay. It's in a fraction of a second. And there's not enough time involved to cause damage to the CTs or the wiring. You're going to interrupt this event quickly. So, the ampacity of the secondary, 5 amps. That gives us our maximum overcurrent setting, a tap of 5. And the maximum setting for this is 1/2 the value, the current ampacity of your ground resistor. 1/2 of that. That's for ground fault. Now we've got a basis there to work on. So what we're going to do is choose a cable, and we're going to adjust this relay to accommodate that cable. And I believe a good one to take would be a 2-aught, 90 degrees C, 15K cable. That's 362 amps is overcurrent setting. These are all listed on the chart. And this chart, this is a state machine. It has the state chart on it. This is what you'll view. You'll have this chart before you if you're to adjust this relay. Okay, 2 aught, 9 degrees C. It says the ampacity is 290. That's an important number. So let's make a note of that. 290 is the ampacity. 290. Now, it's already calculated for the overcurrent setting. It's 125% of the ampacity. That's times 1.25, which in this case would be 362. That's the overcurrent setting. I'm going to mark that as OC. And this one here, I'm going to call that ampacity. Now the next one that we need would be short circuit. Okay? Short circuit, 600% of the ampacity. 600% of this, not the overcurrent setting, but of this. So it would be, using our calculator here, 290 times 6. And that equals 1,740 amps. 1740. Now guys, these are our maximum levels. This is not what you need to set on. This is the most elevated setting that you could possibly choose and remain legal. Now, myself, I'm more inclined to err on the side of the angels, to set at an adequate level, set to where you don't have nuisance tripping, but you don't want to challenge the maximum on these settings. Because let's face it, short circuit, when you adjust a short circuit, you're adjusting how big the fire will get if you have a short circuit, how large the event will be. Now, you don't want to maximize these levels. You can't have it tripping every few minutes, obviously, but you don't want to really challenge this cable. I'm going to set it at the max tack. Overcurrent, that's more or less your monthly budget. Your monthly budget, you have to pay. Some of us have mortgages and power bill and gas bill and telephone, telecable, all these different monthly expenses. That's your monthly budget. That's the one you're going to live under. This is going to be your day-to-day activity. How you run will be controlled by your overcurrent setting. Short circuit, that's more or less fire insurance. Now, you don't have a house fire every month. You want to be protected. If you do have a house fire, you want to be, covered for that, but you don't have a house fire every month. That's short circuit. So we're going to set at maximum levels, maximum available to us on this panel here, but in real life, you don't want to push the envelope. You want to be adequate, but not excessive. Now, first thing that you're going to do to compute this, you need to have your CT ratio. Let's call that CT ret right there. And then you're going to have an overcurrent tap. You're going to have overcurrent actual. You're going to have a short circuit. That's determined with a core. And you'll have a short circuit actual. Okay. Now our goal is to come as close to these numbers as we can without being excessive, without exceeding those maximum settings. Here we go. The first one that you would figure, you're going to automatically choose the magic number 5. That's the ampacity of your CT secondary, magic number 5 for a tap. Now you divide your 362 by 5. What would that give you? A 70. 70 would be 350. That's as close as you can get. But we don't have a 70. All these ratios available, there are two that are missing, the 70 to 1 and the 110 to 1. They aren't available. So the next closest one I can get without going past that would be a 60. A 60 to 1 ratio. Now if I chose tap 5 and a 60 to 1 ratio, my actual setting would be 300. That's not too bad, but we may can get closer. Now after you determine that with a tap of 5, the largest CT that you could have with a tap of 5 is 60, then it would be safe to go ahead and list all the other CTs under this, such as 80, that's your next one, 90, 100, and 120. That's all your available options for this particular cable. So let's have a look on this. If we chose an 80 to 1, we would divide the 362 by 80. That would give us a tap of 4, an overcurrent value of 320. Well, that's better than the 300. That's closer, not necessarily better, but it's closer to our maximum. We'd take our 362 by 90. Well, now, a 4 for how much? 360. Wow, that's really close. How about that? A 362 by 100 is 3. 3 times 100 is 300. And the 120 would also be a 3 for 360. Now, look here, guys. 2 of these are obviously much closer than the others. So if we're going to set at maximum levels here, there's no use to pursue these others that are inferior settings here that are farther away. So let's do this. Let's just strike those. We're not going to consider that one or that one or that one any farther. As far as we're concerned, there are 2 that are tied for first place, and first place, the closest setting, that's what we're after for the purpose of our examination here. So using that, we're going to now use the short circuit core or the short circuit maximum setting to find the core. We use the 1740 in the place of the 362, divide that ratio into 1740. Let's take 1740 divided by 90. That equals 19.333. So let's just round it down to the nearest whole number for a core of 19. Now, 19 times 90, 1710. If I chose a core of 90, a core of 19, a CT of 90, my relay would act upon 1710 amps. Okay, let's try the 120. That's actually pretty close. So we're going to take 1740, divide it by 120. It's 14.5. 14. Round that down to a whole number. 14 times 120, 1680. Well, there you have it. Now let's face it, in real life, the difference in a short circuit event of 1710 a trip and a 1680 trip, negligible. We're talking fractions of seconds, okay? Tiny fractions of seconds. But we're going to prove, competence here, and that we can set it the closest value possible to these. So this would be the one we chose, the 90 to 1 CT. There it is. That's our setting. That's actually how you compute it. That's the whole thing. Okay. Now we're going to make our adjustments here on these various components. Let me lock and tag this. All right, we've locked and tagged out the panel, and we're going to make our adjustment on this relay panel here to accommodate these settings. First thing that we're going to do is choose our 90 to 1 CT. We'll look at the chart. 90 to 1 is C and E. Well, these lag wires coming from our CT are labeled A, B, C, D, and E. The C goes to terminal 3. We're going to move one of our leg wires to terminal 3 and the other one to E. And that would be the proper CT ratio chosen, C and E. Now, we're going to adjust our overcurrent tap. The taps that I keep referring to, overcurrent taps, these are connections on the back of the relay here, and they're labeled. You have an overcurrent tap. These various points are labeled. This one is 2, 2.5, 3, 4, 5, 6, 7, 8, 10, 12, and 16. The tap bar range is from 2 to 16. Now, not all of those numbers are represented between 2 and 16, just the ones that I called out there. So, when you're choosing the tap setting you want to use, make sure that tap is actually available to you. The 4, as luck would have it, we're on tap 4. That's preset for us. That's great. Okay. So we're on tap 4, the 90 to 1 CT. Overcurrent is set. Now, let's talk about this core. This is an adjustable core relay. You know from our prior classes here, we've talked about magnetism. To make an electromagnet, each energized conductor has a magnetic field that constantly surrounds it while it's energized, okay? And to focus this magnetism, you can put a core into the magnet, and that gives a more defined magnetism. Same effect as if you would take sunlight on a piece of paper. Sunlight in and of itself will fade the paper over time, might make it yellow or color it somehow, but it won't consume it. But if you focus that sunlight through a magnifying glass, it will burn the paper. It will burn a hole in it. Well, having a core in a coil will focus the magnetism, and it will make it much more powerful. This relay has an adjustable core, and the core has a span from 10 to 80. This one here has 10 to 80. 80 being the max, and 10 being the minimum. From 10 to 80. That's the range of this device. Okay, 10 to 80. Let's say the span of this device, how much adjustment you have, is the difference between 10 and 80. You have a range of 70 amps that this device will adjust into. So 70 amps between the minimum and maximum. Now when you adjust the core up and down, just imagine this coil on that relay. I'm going to just draw a few turns, and on the actual coil there are hundreds of turns, and you have a core that you can adjust up and down. It's got a bolt. Well, this is the set screw, and a bolt head that you can adjust up and down. You adjust this core in and out of this magnet. Now, the farther down into that coil this bar is adjusted, this rod, this core is adjusted, the least amount or the less current you have to have on the coil to make a magnet of the same strength. All right. If you adjust it all the way down to its 10, then 10 amps flows, it will pick this relay up. If you adjust it up to 80, then it would take 80 amps to flow to pick this up. Now, when I say pick it up, let's, this is a rough drawing, but let's say you have a contact point here. A contact point that when this coil becomes a magnet, the core is magnetized, it will actually lift these contacts and make a contact to operate the relay. So, farther down it's adjusted, the less current has to flow to bring about the same action here, to lift and pick up this relay. That's what we're going to adjust, is that core. How much? There's only two markings on this device. One says min, one says max. On the tag, it says 10 to 80. Now, the only way to truly adjust this relay, because, you know, every relay is not just like another one, the only way to truly adjust it is to use a current generator, you know, and actually drive the CT, put a current on the CT and operate the relay. And you could monitor the current that you're putting on it with an instrument and then adjust the relay for a pickup. Now there are several companies about that can adjust these relays for you. In the field, you may not always have that available to you. And you're going to have to make a field adjustment, a field expedient adjustment. It's not going to be exactly accurate, but you can be in the neighborhood. And if you err, make sure that you err on the side of the angels, you know, and set it at a lower level. Because, like I said, this is fire insurance. You don't have a house fire every day. This is not going to be tripping every little bit. So err on the light side. There are basically 5 increments of measure, and I use the thickness of the bolt head, the adjustment bolt head, as one increment. That's one increment of measure. And there are basically 5 of those between minimum and maximum. So let's divide our span by 5. And that gives you an increment is worth 14 amps. So if I would adjust off the minimum, one thickness of that bolt head right here, that would be add 14 to the minimum, 24. Another thickness, another 14, 38. Yet another one, 52. And the last one, 66. And then we would max out at 80 amps. Now again, this is not an exact science, doing this by field expedient adjustment. This will put you in the neighborhood. You don't want to try to set. I've heard of people counting threads to adjust up and trying to adjust to a fraction of a core setting. Those are very difficult judgments to make, I'd say. If we were going to set it 19, you have 24 and 10, 14 span between them. 9 is just a little more than half that adjustment. I wouldn't challenge that half. I'd choose a point about half the thickness of a bolt head, above 10, and I would adjust my top of my bolt to that point. Tighten the set screw. Again, that's not an exact science. That's not going to be perfectly to trip at 1710 amps. It'll be close. It'll be close. Don't go above it. Don't go way above it. Stay close. If you're unsure, set low. Lower's better. Setting one too low won't get you a violation and won't cause a mine fire. Setting one too high could do both. You know, it could damage your components downstream. Could cause you to be violated or found in violation of the law. So set at a depressed level rather than an elevated level. And that would adjust this relay. You actually turn this set screw until we find a point that we think is sighting at the top of the set screw, directly through to we're about halfway on the thickness of that set screw. And this relay is in the neighborhood. It's pretty close. You put it back in place. The paddle. I didn't mention this before. This paddle, as you can see, it has these multiple bars that go around the paddle. Well, this connects this relay to the circuit. Until you put this paddle in, this relay is not connected. So it's just there, and when you insert the paddle, set it all the way in, now the relay is in play. It's in service. Fellas, that concludes the adjustment of the 51.1 for overcurrent short circuit. Everyone fears all the math, all the calculations. As you can see, there's not really that much to it. It's a matter of laying the problem out, you know, in an orderly fashion, and just do a few simple calculations and you have it. That particular dragon's easy to slay. This one, 50G, we also have to adjust it, and it requires a little math too, a very little math. Now, as I said earlier, we find our levels of adjustment for different cables on this chart, adjust the relay and the CT ratio to accommodate a cable. On this one, there's only one calculation. There's only the ground resistor. There's not a great selection of cables here to choose from. There's one ground resistor. And mostly, it's going to be a 25 amp ground resistor. 25. Okay, as you can probably remember, I told you a maximum setting for the ground fault protection is 1/2 the ampacity of the ground resistor, 50%. So let's divide that by 2. 25 divided by 2. I'm going to make a little notation here, 50%. And that's going to equal 12.5. Here we had all these different ratios to choose from. You've got all these different ratios to accommodate the phases and the different cables to set each phase, you know, all these ratios. The ground has one ratio. There's no selection process there. You have a 10-to-1. Now, if you remember, we divided the ampacity that we wanted by the ratio to get a tap setting. Well, we're going to be setting a tap here too, just like this one. There's a tap. Now the range is different. This one's 0.5 to 2. 0.5 to 2 is our range, and we're going to divide this 12.5 by a ratio of 10. So 12.5 divided by 10, that equals 1.25. Now again, fellas, that's a maximum setting. It's not a recommended setting to set it at, you know, the maximum allowed by law. I've never adjusted one as high as that. 5 amps is a good setting for this. Most everywhere you go, 5 amps will be what you find. The relay is set to trip. If you have 5 amps of current flow on the ground conductor, this relay is going to trip most everywhere. But set it at a maximum level, you could possibly set it at a tap of 1.25 for a value of 12.5. Now, we spoke of the range of the relay. That's listed here, 0.5 to 2. That's on the nameplate. If you take the relay out, just like with the phase, you have a row of taps, 0.5, 0.6, 0.8, 1.0, 1.2, 1.5, and 2. Now these relays are very diverse. You can have, I think the state panel that we used last in testing at the Oak Hill office, and a 0.5 to 4. And so these values will be changed. Whatever tap you're going to set to, make sure you actually have that physical tap. Now I said that we wanted to set at a tap of maximum 1.25. We don't have a tap 1.25. The closest we can come to that without exceeding it is a tap of 1.2. So we're going to loosen this set screw and slide this over to 1.2. And there you have it. We're set to, if this relay will operate when the CT puts out 1.2 amps to the relay, it will operate. The CT is going to have to see 12 amps flowing on the ground conductor. It will put out 1.2 amps to the relay, and the relay will trip and cause the breaker to fall. So there you have it. We can reinstall these. Now these, guys, these are not really a frail device, but they do have to be handled with a certain care. You can't slam them about. Gently put it back in place. Again, it's not connected if the paddle's not in. It's not part of the system, so the paddle has to go in, and that connects this relay that we've adjusted to our system. And that's all there is to setting the ground fault. Okay, fellas, for the last bit of calculation that you do, and the last bit of figuring and math. Now, we decided earlier that, or we spoke of earlier, that the ground resistor has to match the high voltage, application here. Now, the ground resistor needs to deal with at least one phase of your high voltage. If you had two phases grounded, that would be a short circuit, and this relay here would take you out. But the ground resistor needs to be able to convert the energy of one phase to heat. Now, it has to be appropriately sized. So we're going to do the calculation for the ground resistor. Let's say that we have a system 12,470 on our line. Okay, our line voltage, that's three-phase power, and we have a phase-to-phase reading of 12,470. Now we're going to apply the square root of 3 to that 12,470. .73 square root of 3. We're going to divide 12,470 by the square root of 3, and that'll give us a phase voltage of 7208. That's one phase. Now our goal is to have a ground resistor appropriately sized to convert as much of 7,208 volts to heat as possible in the event of a ground fault. So let's use Ohm's law. There's a number of ways of expressing Ohm's law, but they're all going to mean the same. E equals I times R. Okay, that's Ohm's law. Now, I would like you to lay the problem out as such to keep everything in a structure here that you can easily track. We're going to determine the value of these variables. I'm going to make a little legend here to go by and see if our ground resistor is right. Now we know from our discussion earlier that's a 25 amp ground resistor, so the I is 25 amps. And you would need to take an instrument, a multitester, an ohm meter, and read the resistance of the ground resistor. You'd isolate the ground resistor and read the ground resistor with an ohm meter reading. Let's say that this ground resistor, I'm going to arbitrarily pull a figure out, 285 ohms. Okay? So our R figure is 285. Now let's plug in the values on our formula. The E, we don't have a value of. We don't know what this resistor is capable of. But we have a value for I, it's 25. And we have a value for R, it's 285. After we do the math, use your calculator. 25 times 285 equals 7125. So that's the capabilities of that device. If it reads 285 ohms, it's a 25 amp device, the voltage drop on that resistor will be 7,125 volts. Now, we decided that a phase is 7,208 volts. So let's subtract. This is the capability of the resistor, 7125. That's in the Walgreen perfect world. That resistor will deal with 7,125 volts. Well, let's subtract that from what we determined our phase would be. Looky there. There's a difference of, what's that, 83? 83 volts. Now that voltage, that is the voltage external to the resistor in the event of a ground fault. So we would know that under these calculations, that resistor at 285 ohms would leave only 83 volts external. The rest of it would be passed through the resistor, converted to heat. So that would be a legal ground resistor. As you probably did the math, knowing with Ohm's law that every ohm of resistance at 25 amps will be worth 25 volts. So if we would add 3 ohms, make that 288, then this figure would be 7,200 and would leave only 8 volts external. That would be a perfect world. Okay? That's all the math. All the math that terrifies everyone with this relay. That's it. You've set the relay. You've checked the ground resistor. You've found voltage external. And that's the extent of all the calculations that you might have to do. It's unlikely that you would have to set the whole relay for your test. You're going to draw a problem in a lotto fashion, and the state now uses this form, which has each CT ratios. That's just as we do, and they have the tap settings like those in the black, and they have an adjustable core relay just like this one that you would mark your various settings on. They'll give you a cable size to figure. You use the chart. Here's all the ampacities of the cables. Here's the CT ratios, and you just fill in the blanks. That's a really, really simple form. It's much easier now than it was. Okay, to do a monthly check, if part of your test involves to illustrate a monthly examination of a high voltage circuit breaker, this will be what you did. You're going to tell the man, I've made a visual examination of my breaker and its auxiliary devices. I'm going to do a manual operation of at least 2 auxiliary devices. And I'm going to check ground continuity to the furthest point controlled by this breaker. That furthest point can only be one of 2 places. One of 2 places. The furthest point will be the next switch house, the next vacuum breaker, the next relay that you have on this circuit. Or it'll be the end of the line. At the next relay, you have a new ground monitor to take over that section of cable beyond this one. The end of the line is that point in your mind where from this relay, when you follow the cable to its end, it terminates in a box, in a transformer, and there's a high voltage input, but there's no feed through. The cable terminates, the high voltage circuit terminates at this point. That's the end of the line. One of those 2 places will be where you determine you have ground continuity to. Now we're going to do manual operation of these devices. Now this, as well as the ones that you check in real life, you know, as part of your job, has control voltage on these relays. And there's a lot of this relay here that is energized with control voltages, with 110 volts or 120 volts. So we're going to use a non-conductive rod here. This is just a pencil. And wear our low and medium voltage gloves for safety, and do a manual operation. Now, we're going to close the OCB. The apprentice needs to illustrate. I'm going to manually operate my short circuit relay and gently put the contacts together. And when you do, the OCB opens and you have a flag shows. All right, you reclose the breaker. I'm going to manually operate my overcurrent relay. Gently raise the contacts and touch. Opens the breaker. The breaker opened. I'm going to reclose my OCB. I'm going to manually operate my overcurrent time disc. Here we go. We're going to manually operate this time disc. We're going to turn the disc around, make contact on that post, and the breaker opened. That completes the manual operation of one auxiliary device. This device is one device. It has 3 functions that you need to test, but the device, this is 51.1. That's one auxiliary. For our manual operation of our second auxiliary, I'm going to manually operate the ground fault relay. You raise contacts gently, and you saw the breaker open, OCB opened. I'm going to reclose it. I'm going to manually operate my ground fault time disc. Gently turn the wheel around, make this post come in contact with that point. It opens the breaker. Okay, now you reclose the breaker. You can set these flags back by operating this linkage here, and that closes those flags back off. Now keep in mind, these tap settings here, this part of the relay is live. There is control voltage there, so don't put a pencil or an ink pen with something conductive on it that will ground this device. Okay, now the next statement is I'm going to operate my control breaker to simulate a power outage. My OCB should open and remain open even after power is restored to prove that I have under voltage protection. Okay? And you do that just as I said. You have your breaker is closed, your OCB is closed. You manually operate your control breaker. Now, all the lights go off and the breaker has fallen. So you reset your control breaker. The OCB is in an open position. And that proves that you had under voltage protection. Under voltage meaning that if I have a loss of my line voltage 40 to 60%, by definition, the OCB should fall. And it did. That's good. So let's reclose the breaker. The last test. Now here on this test panel on the trainer, the E-stop that you're going to operate to prove ground continuity is right here. But in real life, what you're going to actually be doing as part of your job, the E-stop will be at that farthest point, at one of 2 places, at the next high voltage relay panel or at the end of the line, where you have a high voltage input into a box and no feed through. And you're going to operate the E-stop at the furthest point controlled by this breaker and protected by this breaker to prove ground continuity. Now, a lot of people make a mistake of saying, I'm going to check my E-stop at the furthest point. That's not what you're doing. You're using the E-stop. It's a tool, just as if you were going to use your meter, your multitester, to check the ohmic value of the ground resistor. You wouldn't say, I'm checking my own meter. You're using the ohm meter as a tool to check the value of the ground resistor. You're going to use the E-stop to check ground continuity. So you're going to operate the e-stop at the furthest point, and your breaker opens. And that concludes the testing of the high voltage circuit breaker relays. Fellas, we've come a long way. We've done some calculations, to match a cable. We've checked a ground resistor, and figured its values. We've set the relay for ground fault. We went through the physical checks that you're going to really do these checks in your job, not just for testing. Now, some of the questions that you could possibly be asked, these are questions that I've heard asked, and they're all in the statements of fact that you study for your training manual. You may be asked, what color is the ground continuity monitor pilot wire? Well, it's yellow. You could be asked, what's the minimum size for the ground continuity monitor wire? That's a size 10. What's the maximum voltage you can have on your ground continuity monitor? It's 96. These are all patent questions. They're in your training guide. You can learn these. You might be asked, what's the maximum voltage allowed external to the ground resistor in the event of a ground fault? It's 100 volts. We figured one ground resistor here earlier. You can be asked, what's the industrial standard for the ampacity secondary of a CT such as this? It's 5 amps. That dictates the upper level tap setting for us, 5 amps, the ampacity of this CT. That phase doesn't appear to be connected to the CT. Your answer to that, it's magnetically coupled. Okay? Those type questions there, when you're asked these questions here, this allows you to show that you really have a grasp of the panel, of the protections, of the concept of high voltage relaying, high voltage monitoring. And these are not designed to trip you up. They don't want to try to fail you, but they want to know that you indeed understand what you're being certified for. So just be calm and be relaxed. These same statements, these same questions, the answers, you've drilled them hundreds of times in class. All through your high voltage test, all through your legal requirements, these same questions are part of that text. And here they are in real life. Now, that concludes our setting of the high voltage relays. But let's talk about our safety here for just a bit. Before you're going to do any high voltage work, any high voltage cable work, a termination, a splice, to bring a transformer online, any of these things, you must, this is a must, follow safety rules to the strictest possible level. You want to definitely open a visual disconnect. Now, as you can see, I opened this breaker by pressing that button and a breaker dropped. That's not a visual disconnect. The light is visual. You're pushing a button. You see which button you're pushing, but it's not a visual disconnect. The light indicates that it's off, but you don't see a separation between the conductors, okay? You don't have a visual separation that you can look at and see, I'm disconnected from this source. The vacuum breaker, the contacts they're in bottles, that they're not visible. An oil circuit breaker, the contacts are in a tub of oil. They're not visible. You have to open a visual disconnect. A gang-operated air brake is the most common thing. You're going to open a visible disconnect and actually see the contacts come apart. The next thing, lock and tag. Lock and tag, lock and tag. If you lock this out and you tag it, you take the key with you, and you personally do this, then you know the power is disconnected. Now, after you take the power off, after you lock and tag, it's not considered to be disconnected and locked and tagged and ready for work on a high voltage circuit until you ground it. These phases, you know, cables have the capability of storing electricity as a capacitor would. Transformers, dry type transformers, they have the capability of storing electricity as a capacitor would. Some high voltage circuit have actual capacitors on them. Until you shunt these phases both to each other and to the ground and make everything the same potential. Everything is neutral now. They're grounded. It's not safe. It's not safe. So it has to be a visible, power removed. You're going to break the circuit with the oil circuit breaker or the vacuum breaker. It is designed to extinguish an arc if there is an arc. You know, you have all of your capabilities of breaking the circuit are in the vacuum breaker. After you take the power off with the vacuum breaker or the oil circuit breaker, then open a visible. Look at the visible. Don't just operate the lever and walk. Look at it. Make sure you see 3 contacts separate all 3 phases. And then most of our breakers and boxes here, our switch houses are equipped with a grounding bus that when you operate the visibles, the phases come against a ground bus. But if you don't have that, then you're going to have to manually attach grounds. But either way, easy or not so easy, it has to be done. You have to ground this high voltage circuit before you work on it. Now the last thing, you've opened visibles, your breaker is off, you know, it's grounded. Are you sure? Test before you touch it. You know, test it, make sure the power's off before you touch it. You've done everything you can, but mistakes can be made. Errors. Error's human. Test it before you touch it. And this is not one of those situations where you have an oops, you know. These are life-changing or life-ending events if you make a mistake with high voltage and come in contact with an energized high voltage conductor. Test it before you touch it. Be sure. No. Don't take the word of anyone. You know, it's your life. Take care of it.